The end behavior of a graph is whether or not the arrows at the ends point up or down. So maybe they're both up, or maybe they're both down, or maybe one of each. We're going to figure out how you know which way they point today. We're also going to be able to look at a graph and figure out if the degree is even or odd, and if the coefficient in front, the leading coefficient, is positive or negative. And we're finally also going to graph polynomials. So this is the book definition of end behavior. It says the description of the values of the function as x approaches positive infinity, which we'll use that little infinity symbol, or negative infinity, the negative infinity. All that really means as x approaches positive infinity, it means when the graph goes to the right. That's all it means. And when we see as x approaches negative infinity, that's what we write in math symbols, and all it means is when the graph goes to the left. So we use that kind of notation in future math classes, so I'm just introducing that to you now. Let's fill out this chart. If the leading coefficient, if the first number in front of your equation is positive, and your degree is even, so if the highest exponent is like a 2, 4, 6, etc., then both of your arrows are going to point up. All right? It could be a parabola that connects them. It could be one of those W's that connects them. But I remember even degrees point the same way. And since it's positive, they both point up. If your leading coefficient's negative, then instead of both pointing up, both of your arrows point down. And maybe it's a parabola that connects them, or maybe it's some other type of squiggle. So to read the notation, you would read as x approaches negative infinity, so as the graph goes to the left, the function approaches positive infinity, which means it points up. And as x approaches positive infinity, so as the graph goes to the right, the function goes to positive infinity, so it points up. Now for the odd degrees. This time, if you have an odd degree, the arrows aren't going to point the same way, they're going to point opposite ways. So I always remember odd, opposite. If your leading coefficient's positive, it means that the ending one will point up. I remember that because the slope of a positive line, if you think about it, goes up, up, and away. And so it ends pointing up, which means it starts pointing down. And maybe you have a squiggle like that in between. And again, if you read this, as x approaches negative infinity, so on the left side of the graph approaches negative infinity, see how it goes down? And as x approaches positive infinity, so it goes to the right, the graph approaches positive infinity and it points up. So that's how you would read those symbols. If your leading coefficient's negative, think about the slope of a negative line. Negative lines end up pointing down. So that means the ending arrow points down and the beginning arrow points up. And maybe it's, I don't know, some sort of squiggle between them. That's just an example. And so you always look at the ending arrow. Since that points down, you know it's negative for the leading coefficient. And since that one points up, you know it's positive. So let's use that chart to answer these questions. In A, the leading coefficient is the first number, so -4. The degree is 3, the highest exponent. So we have a leading coefficient that is negative, and our degree, 3, is an odd number. So if you look up here, degree 3 and negative would be right here in this box. So that means that one arrow will point down, the ending arrow, and the first arrow will point up. They're opposites. If you fill out the little symbols, you would put as x approaches negative infinity, the graph goes up, and as the graph approaches positive infinity, as it goes to the right, the graph points down. Really, the next place you'll see notation like that would be maybe pre-calc or calculus. So I'll accept it if you just want to draw the arrows, or I will accept it if you also want to fill out those symbols. So go ahead and try example B. So there's the answer to B. You can check to see if you did it right. The leading coefficient's positive and even, and so both arrows will point up. Again, I will accept it if you just want to write your answer using the arrows, or you can use the symbols. Now we'll do the same type of thing, but this time we'll use the graph. When I look at graph A, I notice the arrows are pointing opposite directions, so I'm thinking odd for the degree. And this one, the ending one, is pointing up, so the leading coefficient must have been positive. When I look at B, I notice that the arrows are pointing the same way, which means the degree is even, and they're both pointing down, so the leading coefficient must have been negative. Go ahead and try C and D on your own. So there are the answers for C and D. Hopefully you can check to make sure you got them right. We'll follow these 5 steps that are in the box at the top that is cut off of this page, but you have it on your sheet. First thing is you're going to find the real zeros by typing your equation into the calculator and y equals and seeing where it actually crosses the x-axis. You can look at the graph or you can go to the table and figure out where they are exactly. So if you do that for this equation, you'll see that the real zeros are at -4, -1, and 2. So right off the bat, I'm going to go ahead and put a dot at -4, -1, and 2. Next, we'll find the y-intercept. The y-intercept is whatever the constant in your equation is. And the constant is always the one without any letters at all by it. It should always be at the very, very end when you have your equation in standard form. So in this case, our y-intercept is -8. So I'll write it down right there, and I'll go ahead and put a dot down 8 on the y-axis. Next, we need to find the local min and max. So up above for step 3, I said that those are the turning points. This is kind of a rough sketch of what you see on your calculator. But local min and max are the turning points. We used to call them the hills and valleys, but it's the top right there and the bottom right there. What's the highest point before it turns around, and what's the lowest point before it turns around? You can find those by pressing the trace button on your calculator, and a little cursor will jump on your graph, and you just use the left and right arrows to scroll around until you can get it on top of where the lowest point and the highest point are. In this case, it's approximately 10 and approximately -10. There's ways to calculate those exactly, but I'm looking for just a very close approximation. So the maximum was in between the first 2 zeros, up 10, so I'll put a dot right there. And the second one, the minimum, was between the next 2 zeros, so about right there. The end behavior we can already kind of tell from the graph, but we know that the arrows point opposite like that because the leading coefficient's positive and the degree is odd. And so now that we have all that information, we just have to connect these dots with our line like that. And we're done. If you don't have a graphing calculator at home, you can go to Desmos.com and type these in the graph. When you type B in, you'll see that there's only one real zero, and that is at 1. So we'll put a dot at 1 on the graph. The y-intercept is the very last number, the constant, the one without any letters next to it. So our y-intercept is -1. So we'll put a dot on -1 on the y-axis. And now with this one, the shape of the graph, it sort of looks like that on the calculator. There is no min or max, because in this case, it goes from increasing to increasing. It doesn't change directions, so it doesn't turn ever. So we can just put NA, not applicable, and NA, because it doesn't turn. And the end behavior we can see on the graph, just like the first one, the leading coefficient is positive and the degree is negative, so the arrows point opposites. So that would be all we could plot for that one. I gave you example C because this is one where if you typed it in the calculator, looked at the graph, and then looked at the table, you wouldn't be able to find any perfect real zeros because none of the zeros would show up in the Y column, which means that the zeros don't go through integers on the x-axis. So for this, what you'll have to do is you can either trace or you can just use the cursor and move it left or right so that you can put the cursor on top of where it looks like the graph crosses the x-axis. In this case, it looks like the zeros are approximately at negative about 2.8, 0.4, positive 0.4, and positive 2.1. So we will plot those. Negative 2.8, so almost to negative 3. 0.4 is going to be pretty close to the x-axis, or I mean the y-axis right there. And 2.1 will be just past the 2. The y-intercept we can find because it is the plain number with no letters, so the y-intercept is 6. I'll put a dot just above the 5. The local max, if you hit the trace button, you could trace and try to see where it turns around. You might need to zoom out or adjust your window, but the highest that it goes before it starts turning around is 17, and the lowest it goes is negative 5. We already know the end behavior is going to be like that because it's like the other ones. It's a positive leading coefficient with an odd degree. So let me put the max and min on there. Between these first two zeros, the graph goes way up to 17. And the local min between these two zeros goes down to negative 5. Now we can connect these dots with our graph. Goes up, turns around, comes back down through the y-intercept and the 0, through that minimum, and then back up through the 0. And you're done. I know this assignment says 1 through 10, but there's 11 problems, so it's really 1 through 11. Good luck.